Today we are looking at the third way to find the rate law of a reaction. Let's review. What was the first way we learned how to find the rate? What were we doing? The rate law? All the what? The crossing out. What was it? What did we need to do that? What were all those steps called, guys? Mechanism. So through the use of a mechanism, we can find the rate law by going to the slow step, taking the reactants, raising them to the power of how many they are, because that's how many of the molecules are bumping into each other to find the order. Okay? Could we find the K from that information? The actual numerical value of K? No, we just wrote K, right? And then yesterday, you did method of initial rates. Not yesterday, sorry, Friday, which was yesterday in class world. And what did that data table look like? What were parts of it that will help you recognize it in the future? Which concentrations are they? The concentrations of the reactants, but it was the initial concentrations of the reactants. And what was in the last column? The initial rates. And so you had multiple experiments, right? And then you picked an experiment where two were kept constant in order to figure out the order of one, and vice versa to figure out the order of the other. All right? So this is what we're doing today, is the third way, and that's doing integrated rate laws. You don't need to integrate to do this, okay? You're given the laws already integrated. I'm going to point out which ones you need to know, which ones you need to memorize and not. There's very little memorization in this. I go above and beyond what you really need to know because I want you to kind of understand where the stuff comes from. So if you look, do we all agree this is a skeleton of a rate law? That's zero order, right? With this particular integrated rate law, we're only going to be able to find the order for things that are 0, 1, or second order, 0 first or second order. We're not going to be able to do this kind of math and do this work for anything beyond this. It's beyond the scope of what we do. All right, so 0 first and second order is all we're going to look at today. And so if I were to integrate this rate law using calculus from time 0 to time t, I would get the following equation. The concentration of A minus the concentration of A naught is equal to negative KT. Well, let's take a look at this. What is all this stuff? What does the little naught mean? Who knows? Initial. So this is my initial concentration of my A. This concentration here is after T time has passed. So I can, knowing the initial and knowing the rate constant, because that's what this is, I can figure out how much reactant is left over at any point in time just by plugging it in and solving. In addition to be able to do this math, and if I were to ask you questions and you have to plug and chug, you're going to have to also be able to graph this data to figure out if the data we have is a zero order. So what I want to do is linearize this equation. Which one of these is a constant, A or A naught? A naught. So I'm going to take that A naught and I'm just going to swing it to the other side of the equation. And now this resembles something that should look familiar. Again, we've linearized this. So if I want to prove data is a zero order, I am going to plot what on the X? Time. And what am I going to plot on the Y? Concentration of A. And I'm going to get a line with a negative slope. And that's one thing I want you to make note of. This is going to have a negative slope. If this turns out to be a perfectly straight line or pretty darn close to straight line, I have a zero order reaction. And I'm going to go through the graphing for 0, first, and second. And you, at the end of the day, are going to plot it three ways. And whichever comes out with the best line, the best fit line, is going to be the order of the reaction. And again, you're only choosing from these three. What else can I get from this equation that I need to do a rate law? I need stuff to make a rate law. You found them on Friday. What? K. Don't we need K? So to find K, if you look, K is equal to actually the opposite of the slope, because we can't have a negative K ever. That doesn't make any sense. So what works in all three of these cases is going to be saying the absolute value of the slope is equal to your rate constant. What if I were to say, hey, tell me what the initial concentration of this reaction was, what would you be able to do? Y-intercept. Doesn't this y-intercept give me the initial concentration? So I could also figure that out as well. So there's a lot of things I can figure out from the graph. What do you need to know? I will go kind of back through everything and explain what part of this you need to know. You definitely need to know what you have to graph in order to prove that a zero-order reaction has taken place. So you've got to know what goes on the axes. And I'm going to show you a shortcut to all of this once I'm through it all. Now, another thing that we have to be able to do, and this is an extra info slide. I don't want you to stress out about this slide. I just want you to write down and kind of try to follow. And that is determining the half-life equation of a zero-order reaction. Now, when I say half-life, what's the first thing you guys think of? Huh? Shelf life? Radioactivity is probably the most common perception of half-lives. And a lot of people think, oh, only things that are radioactive have half-lives. No. By definition, a half-life is just the time it takes half of the original concentration to go away. That's half-life. So we can take the equation we just had and find it in terms of half-life. So the equation we just had was A minus A naught is equal to negative KT. Again, you don't need to know this. I just want to prove a point eventually. Not all reactions are radioactive, okay? So depending upon the order of these radioactive equations will dictate which one is about radioactive stuff. For now, I just want you to define half-life. We said half-life was the amount of time it takes half of a substance to go away, right? So if I had to define at one half-life, how much A do I have left? My A original set, when one half-life passes, how much A do I have in terms of the A naught? Half of it. So are you guys okay with me? Is A being A naught over 2 something you understand, that as one half-life passes? So wherever I see A, I'm going to put in A naught over 2. This is A naught, and this is equal to negative K. And I'm going to call it T1 half because this is at one half-life. So I'm just going to clean this up and rearrange it and solve this in terms of the half-life. And I'm going to get a half-life equation. So how can I clean this up? A naught over 2 minus A naught is equal to what? Just math, guys. Come on. What? I can't hear you. Not negative 2 A naught, no. Negative A naught over 2. This is a half of A naught minus 1. Isn't that a negative half? Okay. So negative A naught over 2 is equal to negative K T1 half. Again, I'm solving for T1 half, so what am I going to do? Divide both sides by negative K. You guys have got to talk. I'm getting frustrated. You need to talk. So if I divide negative A naught over 2 divided by negative K, what do I get? A naught over 2K. All right, and that's what a zero-order half-life equation looks like. Do I need to memorize that? No. I'm going to write that, don't memorize. Because there's ways around memorizing it. The reason I'm doing it is I want to make a point here in a few minutes, right? So if I wanted to know the half-life, I could take the original concentration divided by 2 and multiply by the rate constant. Yes? That's, I just put there because that's not a literal change in the value of the number. It's just at one half-life, we made this assumption. At one half-life, A naught over 2 is equal to the A. Okay? All right. So I'm going to put zero order, to the side and go on to first order right now. Now, this is, again, integrating a first-order rate law from time 0 to time t. And this time, through the calculus of this, you get ln of A minus ln of A naught is equal to negative KT. A lot of people are like, well, where does the ln come from? It's the math. It has to do with that exponent of 1 and how to integrate. I've had some multivariable students in the past they used to have to do a project, and they would do the project on this where they use calculus to actually show where all this comes from. Okay, so this is for a first-order reaction. So if I want to linearize this, I'm going to want to get that constant y-intercept to the other side. Which thing am I going to move over? ln of a naught. So is equal to negative kt plus ln of a naught. So now this is linearized. So in the case of first order, if I want to prove something is a first order rate law, what am I going to plot on the x? Time. What am I going to plot on the y this time? ln of a. And again, I'm going to get a negative slope again. It's important to know which slopes are negative and which ones are positive. So zero order and first order graphs are going to have your negative slopes. If you plot the data concentration versus time and it's not linear, it's not zero order. So then you're going to try and plot it natural log of concentration versus time. And you might get a straight line then. And if you do, it is a first order equation. What is my k is equal to? Absolute value of the slope. And then this time, if I wanted to know the y-intercept, I would find the inverse log, because this is the natural log of a. So I'd find the inverse log of the intercept to find the initial concentration. Okay? All right, so now I know two ways to graph, for 0 and for 1. So moving on, let's talk about this. This half-life you need to know. And then, again, I will go back and tell you what's on the AP sheet, what's not, and all that kind of stuff. So this is an important page. Why is this an important page? All radioactive substances active are first order. So do you see why half-life would be important? All right, so we have to know our first order half-life. So let's go ahead and derive it again. What was the assumption we made? A is equal to, at 1 half-life? A naught over 2 at 1 half-life. All right, so I'm going to do my integrated rate law is ln of A minus ln of A naught is equal to negative kt. So at a half-life, anytime I see A, I'm going to plug in A naught over 2 minus ln of A naught is equal to negative k, and now I'm going to put a little subscript 1/2 because that's at 1 half-life. I made that assumption. All right, now you just need to go back into your algebra drawer, and if you subtract logs, what do you actually do? You divide them. So we end up getting L naught of A over 2 divided by ln of A naught is equal to negative k t 1/2. What does that reduce to? Just guess, it's easy. ln of a half, exactly. ln of 1/2 is equal to negative k t 1/2. I need every single one of you to have out a graphing calculator now, because we're going to do graphing. I want everyone to put in natural log of 0.5 and tell me what you get. And you're going to use it. It's a requirement right now for this course to have a graphing calculator. If you need to borrow mine, you can. You can't leave with them, but you're going to need these for tests and quizzes this unit. So what is the ln of 0.5? Negative 0.693 is equal to negative k t 1/2. So what is t 1/2 equal to? .693 over k. This is one that you're going to use over and over and over again. Okay? The good news is it is on the AP sheet. You don't need to memorize it, but you need to know its existence, and you need to know it's a first order. On the AP sheet, it just says 0.693 over k. It doesn't say, oh, this is a first order half-life. You have to know that this is for first order. Okay? There's a huge difference between this half-life equation and the previous one. Closely look at this, 0.693 over k. Going back to the zero order one, what's different in this one? Say louder. Exactly. Look at this one. If the initial concentration changes, our half-life changes. In first order, initial concentration isn't a factor. which makes sense. Don't we know carbon's 14's half-life, or carbon or uranium's half-life, or all it? So don't you see that in radioactivity, that they have set half-lives? So no matter how much uranium you have, it's going to have the same half-life. No matter how much phosphorus-32 you have, it's going to have the same half-life. And this proves that. And so half-life of a first order does not depend on original concentration. And that's indicative of all radioactive substances. Okay? All right, so let's do our last one, our final, which is our second order. That's the last one we can do. And if we integrate a second order from time 0 to time t, we get the following. 1 over the concentration of A minus 1 over A naught is equal to, this time, it's a positive kT. So if I want to linearize this, I can swing that intercept over, plus 1 over A naught. I get that. So this time, if I were to want to plot to prove something is a second order reaction, what am I going to put on the x? Time, and on the y? 1 over concentration of A, and my slope's going to be positive. You have to know second order is a positive slope, because there's going to be multiple choice where they're going to say, which of the following is a second order reaction? And they'll have graphs, and the only one it could be is this one because the slope's positive. So you have to know about the slope. What else do we know about this? What is the slope equal to? The absolute value of the slope is equal to K, just like in all cases. In this case, the slope's already positive, but absolute value works. Okay? And then if I wanted to find the original concentration, I'd find the y-intercept and do what to it? Inverse it, right? And that's why it's down low. When you flip it, it becomes a big number, right? So, no. Here? Why would you, this A naught doesn't change, so we couldn't graph 1 over A naught. Did I put A naught on the other slides? Well, I might have. I just want to make sure I didn't. No, I didn't. Okay. Yeah, A naught doesn't change with time, so we would never graph A naught. Oh, okay. Well, this is the A naught. I brought it over. It's just there. Okay. All right. So what do you need to know out of all of this as far as what are you responsible for memorizing? On your AP sheet, and I'll write down what you have. Oh, we have to do the half-life. Dang it. Let's do that real quick, and then I'll go back and do the synopsis. So the half-life equation, 1 over A minus 1 over A naught equals positive KT. At 1 half-life, I make the assumption that 1 over A is equal to what? A naught over 2. And that's at 1 half-life, so I put the little half there. I'm going to fix that fraction. What are we going to simplify it to? 2 over A naught minus 1 over A naught is equal to K T 1 half. Then how do I do that subtraction? I get 1 over A naught is equal to K T 1 half, and then divide each side by K. I end up getting T 1 half is equal to 1 A naught K. Does second order depend on original concentration? Yeah, it does. So first order is literally the only order that I don't care how much you start with, its half-life stays the same. You do not need to know how to derive these, because I can get around doing problems if they ask half-life by substituting in something for the original and half that value for here. So what I'm doing is actually doing the same thing, but I'm using numbers, and it's nothing you have to memorize. We can get around it, all right? So as far as what you need to know, so here's what's on the AP equation sheet. I'm going to do it in the corner here. In the kinetic section on that sheet that you have for all tests and quizzes and all that stuff, you've got the following. You see this, L naught of A naught equals K negative KT, and then you've got 1 over A minus 1 over A naught is equal to KT, and then you've got T 1 half is equal to 0.693. That's it. That's all on the sheet. It doesn't say what order anything is or whatnot. But seeing this, do you see how if I see these two, and I know that this is what order? This first one? First, and that second. Do you see how you really don't need to memorize 0? Because what would 0 order be? It's just A minus the A naught, okay? So you really don't have to memorize it. Does that make sense? And the only half-life one they give you is this one. And what order is this one? First. So that's what you have to know, and you need to be able to utilize this. I'm never going to give you a question and tell me the integrated rate law for first order. You're just unfortunately going to have to know to apply looking at this and plugging numbers in and stuff. It's not bad. So let's go ahead and do a little recap of what you have to graph. And I'm going to give you a mnemonic thing to help remember. There's only 3 orders we have to graph using integrated rate laws, 0, 1, and 2. So what do I graph to prove a 0 order reaction? What goes here? Concentration versus time. For first order, we graph ln of concentration versus time. And for second order, we graph 1 over concentration versus time. So you're going to take data now, and you're going to graph it 3 different ways. What do our lines look like? What's the slope on this 0 order? Negative, negative, and positive. In all cases, the absolute value of the slope is equal to the k. And finding the y-intercept is going to vary depending upon what the value of that y-axis is. Okay? Doing this should be totally clear to you. Clear. C is concentration, L, natural log, reciprocal. 0, 1, and 2. And it's always versus time. Got it? So if you know everything on this page, just like that, you're going to be fine. Now, these next 3 slides are just synopses of everything I just did, already typed out for you, okay? So don't freak out. 0, 1, 2. We already did all this. You can feel free to look at it when you're studying, make sure you understand it. How do I apply integrated rate laws not graphically? We're going to do a few of these. I'm not going to do all of them, but we're going to go through and make sure you understand. Anytime you're given a question on how much time would it take for the concentration to go from this to this, or after 15 minutes, how much of my reactant do I have left? Anything that's time-based like that is going to be using these integrated rate laws. So this question says, the decomposition of H2O2 to water and oxygen follows first-order kinetics. With a rate constant of that, calculate the concentration of the H2O2 after 10 minutes if the original concentration is 0.2. So they basically told you, they said it's first order. So we're going to use the first order integrated rate law and plug and chug. So first order, again, you're going to have it on your AP sheet, so you don't have to memorize it, but what was the first order one? ln of A equals negative KT. So I'm literally just going to plug and solve. Which variable am I looking for? That's what I'm solving for, okay? So we're going to plug in everything but that. ln of A minus, my original concentration is 0.200, negative, my K is 0.0410. You cannot ignore the units because our units have to cancel. Do they give me units in minutes in this problem? Yes. So luckily, I don't have to convert it. But if they would have given me seconds or hours, I would need to change the time to match the units on the K. So go ahead. You guys have to practice this with those natural logs. You're going to multiply these 2 numbers on the right side, divide by the negative of ln of A. No, you add. I'm sorry. It's a subtraction. So you're going to add the natural log of A to the other side, and then do e to the power to solve for that A. Larson, you've got to have it. Go get a graphing calculator. You have one? Oh, okay. For the next thing we're doing, I need everyone to have one. All right, so as soon as we get out of concentration, holler. And it's not A, it's actually. Good. 0.133, moles per liter. Now, last period someone did it and said, oh, the answer is 0.374. And I knew immediately that was wrong. Can anyone tell me why I knew right off the bat without even thinking that that was wrong? Yeah, it has to be less than the original concentration. Time is passing. This reactant is being lost. So you need to say, does it make sense? Yeah, because this is less than my original 0.2. So ask yourself, does the number make sense? Okay, so that's how you're going to use these. Let's go ahead and do a couple more. The decomposition of N2O5 to O2 and NO2 follows first-order kinetics. Again, if a sample at 25 degrees Celsius with the initial concentration falls to that concentration in 100 minutes, calculate the rate constant. All right, so this time it's still first order, but this time I'm solving for the K. ln of A minus ln of A naught. So what is my ln of A? That's after the 10 minutes has passed. 1.02 times 10 to the negative third minus ln, my original concentration is 1.25 times 10 to the negative third. I'm solving for K, and what is my time? 100, and you've got to watch the unit on time here. And this is where you guys need to know that shortcut from Friday to get the units on K. I don't know if you remember that from the video. We'll go over it again. But someone go ahead and give me a 3 sig fig K here. We didn't use the 25 degrees Celsius, so we're going to stick with 3 sig figs. What? Good. What does that 25 degrees mean? What is that? Any idea? My K is temperature dependent. So what that means is this K is only good at 25. If I have 28 degrees, I'd have to have a new K. All right? Because what happens when you heat up a reaction you learned in the lab? You speeds them up, so that constant is going to increase with increasing temperature. All right, so shortcut for units. You always do 1 over the unit of time, which in this case is what? Minutes, times the concentration raised to the overall order minus 1. What was the overall order? 1 minus 1. So what happens to that M? Yeah, it's M to the 0, which is 1. It goes away. So the units on this K is per minute, 1 over minute. That's it. So use the shortcut to find Ks like this. It makes life a lot easier. Okay. So these next problems, number 11 says, in problem 9, which is the H2O2 one, how long would it take for half the H2O2 to decompose? What do you want to do? Half. And we're going to use the one that's on the sheet because it's first order. So T1 half is equal to 0.693 over K. And they gave us K in the problem. So T1 half is equal to 0.693. What was it? 0.04. And the units, I have to have the units so I know the unit of time. 1 over minutes. All right, so when I do that, what do I get as my half-life? 16.9 minutes. So it takes 16.9 minutes for half of that substance to go away. Let's pretend you were having a really, really crappy day, and you looked at number 9 and you're like, oh, and you don't even remember that this equation exists. Any ideas of what you would do? You know the K. Right, or do you have to even do that, variables? Yeah, make up numbers. Plug in a 4 and a 2. You've got the K. Plug in a 10 and a 5, whatever. Because what you're doing is what Alex was just saying. You're doing the A naught over 2, but you're using numbers for it. And for some reason, you all are way more successful in using numbers than you are in doing things with variables. I don't know why, but you are. So you can do it this way, too, and you're going to get the same answer. You can do that, and that's why you don't need to memorize those other 2 half-life equations, because if they ask you it for a 0 or second order, you can do it this way. The only reason I'm showing you this one is because it's such a huge component of nuclear chemistry, And they will specifically give you problems for first orders where they won't give you any concentrations or anything. They're just going to say, here's the K, what's the half-life? Here's the K, what's the half-life? That's going to be your most efficient way to solve for it. All right, so be familiar with it and be able to use it. All right, I'm not going to do the math of these. I just want to set them up because in all of these, there's a little bit of an issue. In a second-order reaction, they give you a rate constant, and we know it's second order. I want you guys to find the most common student mistake in this particular problem. No, because that's on the sheet. So let's say they wrote it correctly from the sheet. There's a substitution issue that always happens in this problem. Yes, minutes to seconds. Notice that your K is in 1 over molarity seconds, but they give you 15 minutes here. You cannot do that. That has to be in seconds. So in this problem, they gave you the initial concentration of 0.4, and you are told to solve, oops, I screwed that up. The initial concentration is 0.4, and you are to solve for that guy. I don't need to do it. I just want you to understand that you've got to watch the units here. Okay? And this last one, before we get to the graphing part, I don't know, let's say again, we pretty much addressed this, but in the previous problem, we had K, and it said, the previous one is second order. Calculate the half-life. Well, let's say that we don't know the half-life equation. What am I going to do here? I've got K. It says the initial concentration is 0.4. I'm going to plug in 0.2. That's the trick here. Because it says calculate the half-life. So you take your original, divide it by 2, and then solve. All right? If you knew the half-life equation by heart, I think it's 1 over A naught K, you could do it with the A naught and the K. But since you might not remember that, just remember to divide that by 2. All right, this is where you need to get your calculators out. So I'm going to kind of scroll down, extend this page a little bit. We're going to focus on this problem. In these problems, you guys need to be able to find the rate law and the K. That's what I expect. Okay? So I want you to recognize how this data is different. This data table is different than the method of initial rates table we did on Friday. How is it different? Time and concentration. The other one gave you concentrations and initial rates. Okay? So when they give you time and concentration data, that's when you're going to pull the rabbit out of the hat and start graphing things those 3 different ways that we talked about, that you have those 3 graphs of. Let me talk. Some of you have experience with this, some of you don't. I'm going to talk through it slowly for the first one. If you know how to do it, fine. Go ahead. Just be quiet so you don't disrupt the process for everyone else. You're going to go to, in your TI calculator, Stat, Edit, and open up all your lists. And I'd like everyone to do this the same way, so if there's an error in your processes, I can identify it quickly. All right? You're going to have 4 lists, L1, L2, L3, and L4. We're going to make this as streamlined as possible. In your first list, you're going to put your time data, L1. In your second list, you're going to put just your concentration data. In the third list, you're going to do the natural log of concentration. And in the fourth list, you're going to put the reciprocal of concentration. I will show you how to do a batch transformation here in a second. Okay? Then, you're going to go to, once you have your list complete, Stat, going to Calc. You're going to pick the Lin Reg button, and you're going to do 3 different linear regressions. You're going to do one for a 0 order, one for a first, and one for a second. So you're going to do linear regression. What did you plot for a 0 order? Time and concentration, right? So you're going to do L1, comma L2, and I'll talk about the entry of that in a minute. Then I'm going to do linear regression for a first order, which was time versus what? Natural log, right? So you'll do L1, comma L3. Then we're going to do second order, which is linear regression of L1 comma L4. How do I find out which one? I get an equation of the line. How do I find out which one is the best? Which is the best line? Which line is most linear? R squared. That's called the correlation coefficient. Whichever one is closest to 1, the value of 1 is going to be the best line. So before you start this, a lot of you do not have your diagnostics turned on. So we have to do that first. What I want you to do is go to your catalog, which is second 0. Thank you. Second, and then the 0 button. Now at that point, if you notice, if you look in the top left of your screen, you're in what we call the alpha mode. You see how A is up there? Like in your cell phone, rather than going through the whole stinking alphabet, hit the letter D at that point, and it'll take you down to the Ds. We want to go to diagnostics on. You hit it once, and you hit it again until it says done. At that point, your diagnostics are on. You need diagnostics on for that R squared to come up. Anytime you reset your calculator or change batteries, it goes back to standard factory settings, and diagnostics need to be turned on again. So is everyone diagnostics on? All right. So now go ahead to your lists. You do this in algebra, you know how to get to the lists. And then in L1, put all your times, and in L2, put your concentrations. I'll give you a minute to do that. Then I will talk about the batch transformation to this next one. I love how I got a note that says, immediately, end of period. So I don't know which one. You can wait. I'd wait. Okay. For those of you at home, I can sing a song for you while we wait on these people. La, la, la. Okay. Is everyone ready to roll? Do you have your L1 and L2s in? I just don't want anyone to get behind here. Not finished. Okay. So a neutron walks into a bar. Asks the bartender, hey, how much for a beer? And the bartender says, oh, for you, no charge. I'm just telling jokes because people at home are bored while you guys are entering your values. All right. So to do a batch transformation, rather than having to take the natural log of every single thing one at a time, which is insane, the beauty of the calculator, it does it for you. So I want you to take the cursor and move it to the tippy top of the L3, where the L3 is blackened. The cursor is on top of the literal L3 letter, not the first value in the column. I'm talking on top of L3. What are we doing? We're taking the natural log of which list? L2. So you're going to hit natural log button, and then you're going to hit the second number 2, because see how above the numbers there's L1, L2, L3 above the actual numbers? So hit natural log, second 2, and if you look at the bottom of the list, you'll see it show up. And then hit enter. All of your values from L2 will then be put into L3 as natural logs. Question? You look lost. Take your cursor to the top of L3 till it's blackened and type natural log, second number 2, and hit enter. Now you're going to do the same thing in L4. Take your cursor to the top of L4, and you're going to do 1 divided by L2. And it'll show up. You can either do L2 to the -1, or you can do 1 divided by L2 and hit enter. And that's going to put all your values into that list. Good? All right. So now we're going to do linear regression. The thing about linear regression is it's really hard for you to show your work. So this is my requirement. I require for each order for 0, 1, and 2, I want the equation. You have to write out the full equation and the R squared for every single one of these 3 orders. That's how you show me your work. And then you'll be able to pick which one has the best R squared, and that will be the order of the reaction. So go ahead and start. We're going to do first linear regression to prove it's a zero-order reaction, to see if it is. So you're going to do stat calc, hit the linreg button, and then do L1, comma, the comma is above the number 7, L2, and hit enter. If you're getting something called dim mismatch, it means that your data is messed up in your list and you don't have the same number of data points in each list. But you should be getting now an equation and an R. So go ahead and you jot that down quickly. And now you're going to go and do the same thing again for L1, comma L2, L1, comma L3, and then L1, comma L4 to prove that you have multiple orders. Yeah, X and Y is fine. The only reason I want the equation is so I know you did it. And if you made an error in your list, I can look at your slopes or your y-intercepts and see that the error was in your list. It's easier for me to figure out your errors by seeing the equations. I don't care about scientific form and putting in the right things. This is showing me you did the linear regression. That's the question she just asked me, and I said that's fine. Okay, so go ahead and do the next two. Do you have them all done? All right, so those of you working, keep working. I'm talking to the people at home, so we can wrap this up with the people at home. So people at home, oh, you didn't write down your stuff. Yeah, see, what you did here is you put yourself in a situation now when I want the rate law, I don't see your slopes, right? So you can't give me K. I have to have the equation. I'm not just saying that I'm trying to be funny. I need the full equation. Yes. Yeah, so when you do this, you should have gotten it was first order. Tell me your slope. Five or negative 5? Okay, and then your R squared? 0.999. So for people at home, this was your best line because your R squared was closest to 1, and so the problem stated that we needed to write the rate law. So you would write rate is equal to K, I'm sorry, we have the K, so we're going to plug in the K, is the absolute value of the slope, 3.41 times 10 to the negative 5th. Again, K is equal to the absolute value of the slope times the reactant of N, what was the reactant? NO2, and since we determined its first order, you raise it to the first. You're also responsible for units on K. The shortcut was 1 over the unit of time, which in this case is seconds, and the overall is 1, minus 1 is 0, so it's just 1 over seconds are the units on your K. This is all you're really ever going to be required to do to figure out the rate law from an integration. So now I'm going to close up the video here. I'm going to go ahead. This is going to be an independent problem. I'm going to walk around and help you. I'm going to write down the answer to the next one, and you need to do it to get this answer. The answer ended up for the second problem on this page, the slope ended up being 0.548. It ended up being a second order reaction with an R of 0.9998. This was second order. So the final rate law, rate is equal to 0.548 with the units of 1 over molarity second times NO2 squared. All right, so the rest of you, finish up the first problem and work the second problem. I'm going to be walking around to help you. I just want to turn the video off. What's what? It's to the right. It's the data table to the right. All right. Thank you very much. By second problem, I meant this one right there. Have a good day.